Hey class, I've talked to a couple of you about this problem number 4 from the workshop. It's a pretty tricky one, so I thought I'd go ahead and make the first video of the semester for you guys about this. So as you can see in the situation, what we have is we have a car and a train. Alright, we're told that the car has a length equal to 101 meters, so maybe I'll label that here. It's 101 meters long. Okay. And we're told that it starts from rest. So if you see here in this picture, I've drawn pictures at time 1, time 2, and time 3. So I'm going to label what I got going on in each of those situations, because we're told in the process of reading the question that there's a time 1, when the train first starts going, that the car is lined up with the back of the train. There's a time 2 when the car has caught up to the front of the train, and then a time 3 where it's returned to the back of the train once again. Alright, so let's look at what we got going on here. So the velocity of the train when it starts in situation 1 we know is 0 meters per second. Alright, the velocity of the car in situation 1 is just the velocity of the car, right? We're told it's a constant speed, so it's not going to change. And we're going to define this initial time that we start at t1 as being equal to 0 seconds. Right? We're going to just call our initial situation 0 seconds. Alright. Now we're also going to define the starting location of the back of the train and the back of the car in this case as being x equals 0. Okay? Sounds good. Now let's look at position 2. So now in position 2 we now have a new time. Alright, so we have time 2. We are told that 15.5 seconds have transpired. We can observe that the train has covered some distance. I'm going to go ahead and call the distance d here. And we can observe that the car has gone the distance d plus the distance l, which is the length of the train. Okay, so it's covered a larger distance, and it's still moving with its same velocity because it's moving at a constant velocity, and our train has some new velocity that we don't know because it's undergoing this acceleration. And so we're asked to find what the acceleration of the train is, which is going to be the same in each situation. And then lastly, in position 3, we can observe, I'm going to add a subscript up here, d1, because we're going to have a new distance in situation 3. We can now observe that the train has covered some distance, I'm going to call d2, and the car has also covered this distance, d2, as well, and it still has its same velocity because it doesn't change. Let me clean that up a little bit. The velocity of the car in position 3 is still the same velocity of the car. My equal sign doesn't want to look nice, so. And the velocity of the train is yet a new velocity since it's been accelerating that we still do not know. So when we first look at this, it looks crazy, right? We don't know the velocity of the car. That's something we're asked to find. We don't know the acceleration of the train. We don't know distance 1. We don't know distance 2. We don't know the velocity of the train at any different points in time. We might be able to find it using the times given, but we don't know it straight away. Speaking of the times given, we never wrote this one. T3 was given to us in the problem statement, 32 seconds. Alright, so we got all kinds of things going on here, and so what you're going to end up having to do in this problem is use multiple different equations and solving them together. So let's see how we might be able to do that. First, I will zoom out for us a little bit and scroll down, really mostly scroll down. And what we're going to do now is we're going to look at the car and the train at various different time. So what we're going to do is we're going to look at what we've drawn here. So the transition of the two vehicles from position 1 to position 2, and also from position 1 to position 3. So we'll look at both the train and the car. And in doing so, we're going to be looking at one primary equation of motion. And you can do it a couple different ways. Some of you might have used other equations of motion, and that's fine. But we're going to primarily be using our second equation of motion, which tells us x final equals x initial plus v initial times time plus 1/2 acceleration times time squared. Alright, so looking at starting with position 1 to 2, and we'll start with the train, which I'll write in red. We know that its final position, the distance it travels from position 1 to position 2 in time, is the distance d1, and that's going to be equal to our initial distance, which is 0, plus our initial velocity times time, which is also 0, which equals 1/2 the acceleration of the train multiplied by the time, which we have called t1 squared. So d1 equals 1/2 the acceleration of the time multiplied by t1 squared. Next, we can look at the car. Uh-oh, I hear a train coming through. That's my wife adding some entertainment and background music for us, which is awesome. That's the train sound that she made. Anyway, so the blue is for the car, and the car now, its final position, as we can see, is d1 plus L, and that's equal to its initial position, which is 0. We can see that here. Its initial velocity, which is just the velocity of the car, multiplied by the time t1, plus the acceleration of the car. Oh, I never mentioned that, did I? If we look up here, what do we know about the acceleration of the car? Well, for the entire time, we can observe the acceleration of the car is 0 because it's moving at a constant speed. Bonus, that's easy enough. Alright, so we now have an equation for the distance of the train and the distance of the car. What we can do now is we can combine these two into one equation, because all we care about finding again is the acceleration of the train and the speed of the car. Alright, so I'm going to do that really quickly. I'm going to rewrite this equation as being equal to d1 equals velocity of the car times time minus L. And now what I can observe is I can combine these two equations into one single equation. Maybe I'll do it in green. I can combine these two into one single equation because I know that d1 always equals d1, right? It's the same value, so they're going to be equal to each other. And so, oh, there's the train again. So d1 is equal to 1/2 the acceleration of the train times t1 squared, and that's going to be equal to d1, which I have here as well, which is the velocity of the car times times t1 minus L, the length of the train. Okay, so I'm going to circle this just so we can see. Now we have one single equation that has t1, which we know, L, which we know, the velocity of the car, and the acceleration of the train, the two things we're trying to determine. Oh, well, that's great, but it's one equation with two unknowns. Algebra 101, you can't solve that just yet. So what we need to do then is we need to use position 1 to 3 to do the exact same thing once again and get a second equation with those same two unknowns. So let's look at the train here. The train here covers the distance d2. Its initial position, we're still doing it relative to position 1, so that initial position is still 0. Initial velocity is still 0. So again, you're just going to have 1/2 the acceleration of the train multiplied now by t2 squared. And for the car, we're going to have d2. Now that's the total distance it travels here. Same distance as the train, actually. And now that's just going to be equal to the velocity of the car multiplied by t2. And so once again, we know that d2 equals d2. And so we can once again combine our two equations. So we can write that 1/2 the acceleration of the train times t2 squared is going to be equal to the velocity of the car times t2. And so now we have a second different equation where at and vc, the velocity of the car and the acceleration of the train, are our only two unknowns. We are given the value for the time and L, and so now, after all that fun work, this is why I made the video, we combine these two equations together using algebra, two equations, two unknowns. You can solve for both the acceleration of the train and the velocity of the car. Alright, there's a few other ways you might have gone about it, but this I found to be the most straightforward way. I hope this helps. Hopefully you can solve it the rest of the way. If you have any questions, please let me know. And yeah, I hope you guys have yourselves a box-worthy day. And I think that was maybe the train again from my wife. She says hi. Alright, God bless.